In this video, we'll derive the equation of inductance of three-phase overhead lines where the phase conductors are at unsymmetrical spacings. Now, inductance of a three-phase overhead line with unsymmetrical spacing. Let us consider three-phase conductors, conductor A, conductor B, and conductor C. So conductor A is carrying I current, B is carrying IB current, C is carrying IC current. And since this is unsymmetrical spacing, so the distance between the phase conductors are not same. DAB is not equal to DBC. DBC is not equal to DCA. Since the distance is not same, then the flux linkage of each phase is not same. So psi A is not equal to psi B. Psi B is not equal to psi C, or psi A is not equal to psi C, right? So if the flux linkage of each phase is not same, then the inductance of each phase will not be same. If inductance is not same, that means this circuit is an unbalanced circuit. So this unbalanced circuit will produce unbalanced voltage at the receiving end of each phases. Although Vs, which is the sending in voltage or supply voltage, and Is, which is the supply current. So although Vs and Is is constant for each phase, but due to the variation of inductance, Vr will be varied. As we know, XL equal to 2 pi FL. So if L varies, then the inductance or receiving end voltage for each phase will be varied, right? But we have to restore the balance. So how we can restore the balance of the three phase? So there is a method which is called transposition. By the transposition, we can restore the balance of the three phases, right? Now, transposition of a three-phase overhead line. Let us consider three phases, phase A, phase B, and phase C. So phase A is at position 1, phase B is at position 2, and phase C is at position 3. And the distances between the phases are not same. DAB is not equal to DBC and DBC is not equal to DCA, right? As we know, the value of inductance of phase conductor is changed with the distance or with the position, we can say. So transposition is such a way that each of these phase conductor, phase A, phase B, and phase C, each of these phase will occupy each of the position at a certain interval of transmission line length. Let's say phase A is at position 1, so it will occupy position 2 and position 3 after a certain interval of transmission line length. Similarly, phase B, it will occupy position 3 and position 1 after a certain interval of transmission line length. At the same time, phase C, which is at position 3, it will occupy position 1 and position 2 after a certain interval of transmission line length. Let's say we assume this is a 3 kilometer length transposition cycle. So until this is 1 kilometer. So as there are three phases, so we divided the total cycle into three parts. Until this 1 kilometer, until this second 1 kilometer, and until this is third 1 kilometer, right? So let's say initially for the first 1 kilometer, conductor 1 is set at a position 1 with 30 millihenry inductance. Similarly, conductor B is set at position 2 with 20 millihenry inductance, and conductor C is set at position 3 with 10 millihenry inductance, right? Now for the second 1 kilometer, so this is first 1 kilometer. For the second 1 kilometer, we change the position of conductor 1 from position 1 to position 2, right? So this is position 2, this is position 2. So when we change the position of conductor 1 is at position 2, then the value of inductance of conductor 1 will also change. It will occupy the inductance of position 2. So what is the inductance of position 2? It is 20 millihenry. So after changing the position of conductor A from 1 to 2, it will change its inductance value from 30 millihenry to 20 millihenry, right? Similarly, conductor B is changed from position 2 to position 3, so its inductance value will change from 20 millihenry to 10 millihenry, right? Similarly, position 3, the conductor C, its position will also be changed from position 3 to position 1, so its inductance value will change from 10 millihenry to 30 millihenry, right? For the third or last section of the transposition cycle, the position of conductor A is changed from position 2 to position 3, so it will occupy the inductance of position 3, that means 20 millihenry to 10 millihenry. Similarly, conductor V, its position is being changed from position 3 to position 1, so inductance value will change from 10 millihenry to 30 millihenry, and conductor C, its position is changing from position 1 to position 3, so it will occupy inductance value 20 millihenry, right? So every 3 kilometer of the position, each phase conductor will be repeated, right? And if we see the interval transposition cycle, then we can see that each of the phase conductors is getting the position of each of the phase conductors, right? That means the inductance of conductor for a whole length, let's say for position 1, it will have 30 millihenry. For position 2, it will have 20 millihenry. For position 3, it will have 60 millihenry. That means the average inductance of each of the conductor will be same, right? Let's say for conductor 1, we are getting total 60 millihenry. Similarly, for conductor B and conductor C, we will also get the 60 millihenry inductance. Since conductor B, it is also occupying all the positions. Conductor C, it is also occupying all the positions. Occupying all the position means it will get the inductance of that position. So at the end, the sum of the inductance from all the positions will be same for each of the conductor, right? So that means we are getting the equal value inductance for each of the conductor. So the inductance value is being balanced through the transposition, right? Now, what will be the average flux linkages of each conductor? So the average flux linkages of conductor, let's say conductor A is equal to flux linkages of conductor A at position 1 plus flux linkages of conductor A at position 2 plus flux linkages of conductor A at position 3 divided by 3, right? So this is the average flux linkages of conductor A. So we can write psi A equal to psi A1 at position 1, psi A2 at position 2 plus psi A3 at position 3 divided by 3 Weber turn per meter. So what will be the flux linkages of conductor A at position 1? So if we consider A, B, C in a group, then we know the equation, the flux linkages of a single conductor in a group of conductor. So from that equation, we can get the flux linkages of conductor A at position 1. So when conductor A is at position 1, what is the position of conductor B and C? So conductor B is at position 2, conductor C is at position 3, right? So we can write psi A1 equal to 2 into 10 to the power minus 7 IA. So current IA is flowing through the conductor A, current IB is flowing through the conductor B, and conductor C is carrying IC current, right? So this is IC current, this is IB current, and this is IA current, right? So psi A1 equal to 2 into 10 to the power minus 7 IA ln of 1 divided by r prime. So r is the radius of each phase conductor plus IB. So this is the effect of conductor B current, that is IB, ln of 1 divided by D12. D12 means distance between phase A and phase B, right? So when phase A is at 1 position, that time phase B is at 2 position, right? So the distance will be D12. Similarly, for IC current, flux linkages of conductor A will be IC ln of 1 divided by D13. So when A is at position 1, D is at position 3. So the distance between conductor A and C is D13, right? Similarly, for flux linkages of conductor A at position 2, so when A is position 2, that time conductor B is at position 3 and C is at position 1. So the flux linkages will be psi A2 equal to 2 into 10 to the power minus 7 IA ln of 1 divided by r prime, IB ln of 1 divided by D23. So the distance between A and B is 2, 3, right? D23 plus IC ln of 1 divided by D12. So the distance between conductor A and C is D12, right? Weber turn per meter. Similarly, the flux linkages of conductor A, when it is at position 3, that time conductor B is at position 1 and conductor C is at position 3. So the equation will be psi A3 equal to 2 into 10 to the power minus 7 IA ln of 1 divided by r prime IB. So what is the distance between A and B? Now it is D13, right? So we can write D13 here plus IC ln of 1 divided by D23. Why D23? Because the distance between A and C is D23 now. So this is equation number 4, right? Now after putting the value of psi A1, psi A2 and psi A3, we can get the average flux linkages as 2 into 10 to the power minus 7 divided by 3 IA ln of 1 divided by r prime plus IB ln of 1 divided by D12, D23, D13 plus IC ln of 1 divided by D13, D12, D23. Again, IA is equal to minus IB plus IC, or we can say IB plus IC is equal to minus IA So we can replace IB plus IC in this equation is equal to minus IA, and after replacing IB plus IC is equal to minus IA, we get the equation of flux linkages like this. Psi equal to 2 into 10 to the power minus 7 divided by 3 IA ln of 1 divided by R prime minus IA ln of 1 divided by 3 divided by D12, D23, D13. So we get this equation after that, and we can replace the cube root of D12, D23, D13 as D equivalent, which is called the equivalent equilateral spacing, right? And R prime we can write as ds. So at the end the equation will be 2 into 10 to the power minus 7 IA ln of D equivalent divided by ds. So after getting the flux linkage, we can easily determine the average inductance of conductor A. Just divided this by current IA, right? So we get LA equal to 2 into 10 to the power minus 7 ln of D equivalent divided by ds, right? Now since the flux linkages of each conductor, average flux linkages of each conductor is same, then the average inductance of each conductor will be same, right? So LA is equal to LB is equal to LC, right? Now here is a problem, a single circuit of three-phase conductor, phase A, phase B and phase C, and the distance between phase A and phase B conductor is D12 is equal to 20 feet. For phase B and C, D23 is equal to 38 feet, and the distance between phase C and A, D13 is equal to 20 feet are given. The conductors are ACSR Drake type, right? Now find the inductive reactance per mile per phase. So the equation to find the inductance is L equal to 2 into 10 to the power minus 7 ln of D equivalent divided by ds. So we know the value of D equivalent. D equivalent is nothing but the cube root of D12, D23, D13, right? And ds is equal to GMR, geometric mean radius. So here the radius is not given, but this value for ACSR Drake we can find from the data sheet for transmission line. So data sheet is given at the end of this presentation. So from there we can find the value of GMR, which is for ACSR Drake is 0.0373 foot, right? So we can get the equivalent through this equation. We got ds as 0.0373 foot. After putting the value, we can get the value of inductance, right? Then after getting the value of inductance, we can easily determine the inductive reactance. This is 2 pi FL, F is given as 60 Hertz. So this value will be calculated as inductive reactance per foot per phase, right? But after getting this value, we have to change from per feet per phase to per mile per phase. This is very important. We must do conversion, unit conversion. Now here is the data sheet for ACSR conductor. So there are different types of ACSR conductor. So here is the Drake type, and for this type the value of GMR, which is ds, is given as 0.0735, right? So sometimes in the question the type might be changed. Suppose here ACSR Drake. it might be ACSR ostrich, it might be ACSR lark, right? Then we have to put the respective type GMR value. Suppose for a lark type it is 0.0277. For ostrich type it is 0.0230, right? So don't worry about the type. So data is given here. For any type you can determine the inductive reactance or inductance, right?